this lunchtime ITA Cork information webinar titled Moving to IPv6, and we're here with two resident experts in this field, Nick Hillard from INEX and Jerry Sweeney from CloudCIX. So we're going to discuss this subject matter in a little bit more detail, and I'll let the experts to delve into that in a little bit more detail. By way of introduction, my name is Owen O'Mahony and I am the cluster manager with ITA Cork. For those of you who may not be familiar with ITA Cork, you can just visit us on our website itcork.ie to find out a little bit more about our events and the type of initiatives that we run. So it's really a pleasure to welcome you all here this afternoon for this lunchtime session. Excuse me. Now, before we start, just some useful tips so you can really get the most out of this webinar this afternoon. We are recording this session and we will make the recording available in the next week or so. We'll make it available on our website and our social media channels. And during the webinar, we will also issue some audience polls. So we'd appreciate if you can engage and respond to those audience polls. Your input and feedback is very important to us. So please respond to those audience polls. There is also a Q&A tab, and some of you I see are using it, so thank you for submitting questions. And there's a chat function here. Preferably, if you can use the Q&A tab to submit any questions you have to Jerry or Nick. That'd be great. Jerry and Nick are happy for you to submit questions as they are doing their slides and as they are doing their presentation, and I will monitor the questions coming in and put them to the presenters. We'll get to as many questions as we can, so please bear with us on that. So without further delay, I'm just going to ask the panelists now to introduce themselves. So Nick, you're up first. I might ask you to introduce yourself, and then I'll just ask Jerry to introduce himself.
Hello, everybody. My name is Nick Hilliard, and I'm Chief Technical Officer of INEX.
Thanks, Nick. Jerry, over to you.
Hi, my name is Jerry Sweeney, and I'm the Managing Director of CloudCIX Limited.
Excellent. Okay, so there are two parts to this webinar today. Nick is going to give an overview of IPv6 and I suppose give the state of play of where it's at, and he has an excellent few slides prepared on that. So Jerry is then going to go into a little bit more detail from the technical side and on the implementation side. So over to you, Nick, first, if you'd like to present your slides.
Great, thanks very much, Sean. So I want to give an introduction to IP version 6 and talk a little bit about where it comes from, kind of what it's doing, and where it's actually all going to. First of all, just a little bit about INEX. We're an internet exchange point. And an internet exchange point is a bit of an odd sort of organization. We are what you might refer to as a carrier's carrier. We handle internet traffic on a wholesale basis for large-scale service providers only. And we allow them to exchange internet traffic on the island of Ireland. It's a member-owned exchange. There's about 105 paying members. We push quite a bit of traffic. You can see there that at the moment we're pushing about 500 gigabits a second of peak traffic, about half terabit. That is increasing rapidly. Last year it was only about 300, so it's quite a growth area. We have three infrastructures. We don't just have two infrastructures. We have two of them in Dublin, spread over 6 locations, and we also have a local infrastructure in Cork serving the Cork and southern region of the country. And in terms of IPv6, we've been running it since 2003, so we're very much on the early adopter side there. It's important for core infrastructure providers in the country to support this sort of thing at an early stage. Because unless you have it in core, you can't build IPv6 out to end users, which is really what it's all about. So just to start off with where it all came from, the internet is actually quite old, and it originated from a United States Department of Defense project called ARPANET. Now, ARPANET was the Advanced Research Projects Agency, and they were a research facility in the US. And there's a lot of people who say that, well, you know, the internet was built in order to withstand, you know, nuclear attacks and stuff like that. And possibly it was in the back of people's minds that, you know, maybe we ought to look at a network like that. But really, it wasn't set up for that. It was set up to allow people in the research community, in both academia and in the defense research areas, to be able to use each other's computers. And, you know, this is a slightly odd concept because everybody has like about 50 computers at home. I mean, I turn on my Wi-Fi monitor at home and there's like about 15 or 20 devices on it. What they are, I actually couldn't even tell you at this stage. But in those days, computers were big, expensive, lumpy things, and they might have taken up the space of a large deep freeze for the smaller ones, up to, you know, an entire room for the larger ones. So it was important because they were such expensive units, and because they ran such customized software, it was important for people to be able to communicate together. But the state of networking at the time was that if you wanted to connect two locations together, you had to build a circuit. You had a fixed endpoint, and you had a fixed starting point and a fixed endpoint. And this was a very inflexible way of handling things. And it was realized at a very early age that if we wanted to move past this as a sort of a paradigm for, you know, handling multi-user access to computers, it was going to have to change. And two very important concepts were invented at the time. And we look at these concepts today and we think, well, you know, hey ho, that's, you know, boring and normal and everything. But at the time, they were not boring. They were very contentious. And they were very novel. And those two concepts were packet switching and host addressing. Now, the whole idea of packet switching is that instead of looking at networking from a point of view of point A to point B, you would have this idea and then sending down a stream of data, a little bit like, say, X modem or Y modem or UUCP or something like that. Instead of looking at networking from that point of view, you would split up your streams of data, and then each stream of data would be, or at least each individual packet of data would be sent from a start point to an end point, and it would make its way there in any way that the network saw fit. And this was a complete revolution in the 1960s, and there were an awful lot of people who felt that this was an entirely insane way of handling data. It was unreliable. It was a very contentious issue. The second issue was host addressing, which is kind of what we're going to be talking about today. Now, host addressing got away from the whole idea of a fixed starting point and a fixed end point on your networks, which is to say the A and B end of a circuit, to this idea that individual computers could have a host address, and you could have one computer in location A with a host address of host address A, talking to another computer in location B. And it didn't matter where the locations were. Somehow all of that would be abstracted away. What you would end up with was host A with address A talking to host B over address B, all of the data being packetized and switched independently, and somehow the computers would make all of this magic work. The original protocol used for this was a system called Network Control Protocol, and it was a little bit like what we call TCP today. And I've made a note here that it had problems scaling beyond hundreds of computers, and of course, hundreds of computers is a ludicrous concept today. You know, but even still, at that time, this was, you know, it was a huge thing. So they realized in 1969 that they were going to need a new protocol in order to work around these limitations. So they started developing that. It was originally called TCP/IP. The TCP bit was the replacement for NCP, the Network Control Protocol, and it was designed by two people, Vint Cerf, who's still knocking around the internet today, and another guy called Robert Kahn. And they set up that research in the early 1970s. And the idea that they wanted to promote was what they called an intranet. Instead of ARPANET, which was the Advanced Research Projects Agency, they wanted to create a network of networks where you could have multiple independent networks and they would all communicate together. They had what we call a flag day. And that was a day where everyone cut over from NCP over to TCP/IP. And that day was January the 1st, 1983. And because they were moving to a new protocol, they designed the addressing space to be completely ridiculously large. I mean, there were going to be 4.3 billion devices. I mean, who would ever need 4.3 billion devices ever connected to any network? I mean, it was a ludicrous concept. But they realized that the network component of this was complicated. How do you actually set up the routing elements of a network to make all of this work? And this was hard. It was hard computationally and it was hard theoretically. And they handled this by dividing network into what we call classes. And a lot of people will have heard of Class A, Class B, and Class C. Class A were the very large networks. And for IPv4 addresses, we have 1.1.1.1. We see the remnants of that today. Apple up in Holly Hill will still use 17.x.x.x. And all of these Class A addresses were assigned to an individual organization. There were only 127 of them, but yet that was half of the internet address space available. For medium-sized networks like universities, you had Class Bs. So for example, UCC had its own Class B. Other universities around the country had their own Class B as well. And if you were really kind of piddly small, you'd have a Class C. And that only gave you 255 IP addresses, but there were 2 million. And I mean, imagine that. I mean, 2 million networks connected on the internet. It was crazy talk. Far bigger than they ever imagined it was ever going to be. So moving back a little bit again, what is an IP address? Well, an IP address is actually just a number. And in the case of IPv4, an IP address is a number between 0 and about 4.3 billion-ish. And you can tell that this is a very specific number. It's not a number plucked out of a hat. It is 2 to the power of 32 minus 1, which is to say that we have 32 available bits, and that's the number of, that's the decimal equivalent of 2 to the power of 32. We use 32 because it's 4 bytes of data of 8 octets each. And it's a convenient number because it fits in computer CPU registers very easily. And you can calculate and run data processing and numbers like that at an extraordinarily fast rate. So that's why that number is chosen. This is an example of an IP address. This is one of the name servers we use at INEX. And it's composed of 2 parts. It's composed of a network bit and a host bit. Now, the network bit is 193.242.111, and the host bit is .162. And of course, because we're technical people, we love having a little bit of jargon. Everybody likes their jargon, their own impenetrable language that, I don't know, somehow seems to exclude everybody else. And in this case, we call the network bit the prefix, and the host bit the host ID, the host identifier. So you can see that an IP address actually is a little bit more subtle than just a number. It actually codifies 2 things. And the network bit identifies the location of the host on the internet. So nobody else in the world is using 193.242.111. anything in that range is INEX, and that's the end of the story. If somebody else starts using it, we can jump up and down and say, you guys over there, you've got to stop this. This is not okay. But within our own network, we can say that, well, look, we're going to assign 162 for a name server. We're going to assign .163 for a network time protocol server. We're going to put a web server on it, and so on and so forth. And we can subdivide up the entire network into that way. And the routing component of the internet uses the prefix. So when we talk about how to get all of these individual packets from A to B, all of those calculations about how to work that, which are done using huge big routers on the internet, capable of transferring hundreds of gigabits per second, even thousands of gigabits per second in some cases, all they look at are prefixes. They don't really care about the host ID. That's completely irrelevant to them. And using the information contained in the prefix and the separator, which separates out the prefix from the host ID, they can work out how to get from A to B across the internet. And that is truly the internet, the magic of the internet. But there was a problem with this. And the problem with it was that, a little bit like our modern era, where we find Snapchat and Instagram and Candy Crush and everything else hugely compelling, and in fact more addictive in some ways than hard drugs. Everybody who ever touched the internet in the late 1980s or the early 1990s was instantly hooked. They were complete converts. It was completely compelling, and even though we didn't have the things like the World Wide Web at that stage, it was still completely compelling. I mean, you could do things like, talking to people real time and downloading software. I mean, this was completely unheard of. And it was very clear that not only was the usage increasing, the rate of increase of IP addressing assignment was increasing at rates that were completely unexpected. It was expected that, 2 million Class C networks was only ever, would do far more than the lifetime of what humanity would ever need. But by 1992, it was clear that not only was it not enough, it was actually going to run out very soon. So at that stage, Vint Cerf and Robert Kahn and lots of other early giants in the internet had actually handed over control of the internet protocols to the ITF, which is the Internet Engineering Task Force. That was instituted in around maybe 1986 or thereabouts. And they looked at this problem very carefully, and they realized that two things were going to have to happen. And the first thing was that the whole idea of classful IP addressing, like Class A and Class B and Class C, all of that was going to have to be thrown into the bin because it didn't work. It simply was not feasible to have an organization like MIT, which had a population of whatever number of tens of thousands of people, to have a 0.5% of the entire internet address space that was ever going to be assigned ever to anyone. It just wasn't scalable. The US Department of Defense had 13 Class Cs. I mean, this was a staggering amount. That actually constitutes 5% of the usable IPv4 address space. But even still, they realized that this wasn't going to be enough. So they built, or at least, in fact, another company built this very early product called a PIX. And PIX implemented network address translation. And PIX was later bought out by Cisco and became ASA firewalls. But it was very early technology that came from the industry. And was standardized at a very late stage, but it allowed us to mask the effects of exhaustion of internet address space. But even still, the ITF realized that we are going down a path of no return, and eventually the train is going to reach the end of the tracks, and what happens after that? Well, they figured, okay, we need more addresses. So they started work on a protocol, or at least on a process, to design a new protocol. And initially they called us IP Next Generation. Of course, they were all Star Trek fanatics at the time, as everybody was. I certainly remember what you call it in my student digs in Toker, being absolutely glued to Star Trek episodes at the time. And in 1995, they formally specified the definition of IP version 6. And instead of 2 to the power of 32 internet addresses, they had 2 to the power of 128. Now that's not 4 times the amount of address space. That is 2 to the power of 96 times the amount of address space. And if you were to write out that number, 2 to the power of 128, you would get a 39-digit quantity. It's an enormous quantity, completely enormous. But of course, engineers, being engineers love going overboard, and this was unconstrained overboardism. And they decided, you know what, we're going to fix all of these other problems. We're going to deal with security, we're going to deal with local host resolution, and we're going to throw away ARP. And they decided, you know what, NAT is absolutely vile, and we want to dispense with the idea of NAT as well. And we want to build this completely flexible protocol framework structure. Backwards compatibility, they figured, you know what, we had a Flag Day in 1983 and it kind of worked, so maybe we can hope for a Flag Day in the future and that'll kind of work as well. Oh my goodness, that didn't work. Here's a little bit of a tidbit for you, by the way. This is, I believe, the first IPv6 packet sent, or at least the first IPv6 connection within Ireland, and the first IPv6 packet sent outside of Ireland. You can see the date there, it's 1997. We're still here 23 years later, thinking, you know what, we actually really need to deploy this in anger in a very large way at this stage. And it didn't get deployed because of this backwards compatibility issue. And the backwards compatibility issue overrode all of the other advantages that we ran into with IPv6. It made it a very difficult proposition to get people to sit there and actually spend the time to actually make everything work. And of course, humanity, as we've seen recently with the coronavirus epidemic, humanity is a crisis-driven species. We only react when there is a crisis. And we have a crisis now because the reality is that IPv4 addresses are becoming very expensive. They're now about $25 to $30 per IP address. 6 months ago, they were $17 to $19 per IP address. So even in the last 6 months, we've seen an explosion in costs of about 50%, which is an enormous expansion in costs. And we can project that in the future, IPv4 is going to become more expensive than IPv6. We know this because 5G, Internet of Things, even regular deployment of IPv4, or at least of internet connected applications, all of these things require huge quantities of applications. It simply doesn't make sense for me to use public IP addresses on my network at home, even though I would like to do that. And instead, I have to use private IP addresses. I lose functionality because of that. So we've done a lot in the industry. We've done a lot of low-hanging fruit, which is to say home DSL. You can get a service provider like Aircom or like Virgin Media to roll this out over a very large-scale network and deploy it to hundreds of thousands of people at the one time. Very large content providers have deployed this. Cloudflare has deployed this. Google, Akamai, Microsoft. There's been a huge amount of work in all of those areas, and many others. Apple, the same. However, there is a long tail of deployment, and that long tail is very difficult and very expensive. But it is going to become more expensive for that long tail to operate in an IPv4 only environment if they don't deploy IPv6. So in terms of how to deploy, I think most people here will be either looking at it from an enterprise deployment point of view or a hosting deployment point of view, which is to say, how do you build IPv6 into your office, and how do you get your website up in IPv6? And the answer is, well, for your website, you talk to your provider and you say, please turn on IPv6, and they should be bloody well able to do it. And if they can't, you need to ask them why not. And if they really can't, you need to move hosting provider, or you need to consider moving hosting provider. But get the pressure on them to do this, because it's actually important. If you don't do this, people go through network address translators, they go through host mangling systems, and it causes a lot of problems. And for your enterprise system, get your IPv6 addresses from your provider. They will be very happy to assign them either statically or dynamically. Do some pilot runs, do a bit of test familiarization, and do a phased rollout. It's not terribly hard, it's not terribly expensive, but it is strategically important for the long term. So that's all I have to say. So if there are any questions, I'd be very happy to hear them. I think there's a couple of questions here.
Excellent, Nick. Thanks. There are indeed 2 questions for you from Jerry Kelleher. First of all, how do companies know that an address has been taken? And secondly, what about IPv5 and why was this skipped?
Okay, those are good questions. So the first question is, how do you register IPv4 or IPv6 addresses? And the answer is, we have global internet registries. There is a canonical source of internet addresses, and that is the Internet Assigned Numbers Authority, IANA, and that is run by an American corporation called ICANN, the Internet Corporation for Assigned Names and Numbers. And IANA delegates that geographically to various organizations around the world. In the European region, in fact, everywhere from Greenland to Vladivostok and down as far as the Middle East, all of that is handled by an organization called the RIPE NCC. And they handle internet addressing for about 1.2 billion people. So it's a pretty important function. And they are very dedicated to ensuring that anybody who is registered on their database is the accurate internet address holder for a block of IPv4 or IPv6 addresses or other types of internet resources. So the next question is about IPv5. What happened? Well, that's an interesting question because in fact, IPv4, or what we used to call years and years ago TCP/IP, this was only one candidate, and it was kind of seen as a bit of an upstart. But there were plenty of other global networks at the time. IBM had its SNA network, you had DECnet networks, and there was a huge hoo-ha with the OSI, the Open Standards Initiative, and CCITT to create a global internet addressing. And some of us have heard of the OSI model, the 7-layer OSI model. Why they chose 7 layers is beyond me. Maybe it was numerology, maybe it was something else, because it bore very little relation to reality. But there were a lot of competing networking standards. And even in the internet address, even in the internet standards development, we had lots of other candidates. We had Tuba, we had internet addresses for there were a whole bunch of them. I'm running short on names, but there were at least 5 or 6 of them. Some of them sort of got standardized a bit. Others were just, oh, that's a nice idea, but it'll never run. So ICANN, or at least IANA, actually has a registry of internet addresses, and Internet IP version 4 was actually the 4th version of the TCP/IP protocol that actually worked. And then they had version 5, which is thrown away, and version 7, which is another experimental standard. And I think maybe we're up at around 11 or something like that. So it's constant development, and as with any development process, lots of ideas, most of them are thrown in the bin. And I think that's actually a very healthy way of handling things.
Okay, excellent. Thanks, Nick. I'm just a little conscious of time, so I think we'll move on to the next presentation from Jerry. I know there are more questions coming in. We will try and get to them at the end. If we don't, maybe we can try and respond to them afterwards directly with the attendees, but we appreciate you getting your questions in. I'm just going to launch our first audience poll, and then I'll hand you over to Jerry. So please just take a few seconds to review the audience polls and interact with them. And I'll now hand you over to Jerry, who's going to, I suppose, talk from the tutorial point of view, binary and hexadecimal addressing. This is the real nitty-gritty to help you and your organization to get ready for IPv6 and more specifically on the implementation side. So over to you, Jerry.
Okay, thank you, Nick. That was fascinating. And I didn't actually know that you were the first person to send an IPv6 packet in this country. So I feel honored to be in your company. Well done. Will I go ahead, Owen, or will I wait for the
No,
poll to complete?
please do, Jerry.
Okay,
Thanks.
great. Okay. So, so the idea for this talk came out of something that was happening in our organization here inside in CloudCIX. So a couple of years ago, we used to have junior employees joining the company, and they would, as part of their induction and training, I would talk to them about IP addressing and I suppose a bit of number theory behind it. And we saw it as something for people that were joining the company and starting out. But after a little while, some of the senior people that were in the company said, can we sit in on this? And I said, but you use this every day. Okay, you know, are you sure you want to sit in? It's a waste of a half an hour of your life. And they said, no, we want to sit in. So I started doing this, and pretty much everybody in the company has kind of been through it. And people say that they get something from it. So what I'm going to do today, the objective is in 25 minutes time or 20 minutes time, I'm going to show you how we adopted IPv6 in this company. If I started off by showing you this and you weren't familiar with the theory behind it, then that slide would make no sense. So I will judge the success of the talk on the basis of whether you can understand the last slide. I think that's the best way to put it. So I don't seem to be, okay, I can advance my slides now. So we're going to talk about numbers for a little while, and we all learned numbers when we were in school, and what I'm addressing here is 3rd, 4th, 5th, 6th class numbering. So I'm going to start out with this, and I'm going to try, as we deal with other number systems, I'm going to try and bring you back to something that you're familiar with. So we're looking at a number there, 2,684. And what does that mean? It means we have 4 units, we have 8 tens, we have 6 100s, and we have 2 1000s. So 10 to the 0 is 1, 10 to the power of 1 is 8, 10 to the power of 2 is 100, and 10 to the power of 3 is 1000. And then we learn to manipulate numbers by the concept of carries. So you learn your addition, 5 plus 4 is equal to 9. And then you go on to more complicated addition, 123 plus 345 is 468. And then in 4th class, you start doing your carries. So 9 plus 6 is equal to 15. How do you deal with 15? You have a carry. What that means is that you have 110 plus 5 units, and you carry the 1. Now, we all know that, but I will try and, as we do anything, I'll try and bring it back to that, because that's a base that everybody understands, and that's the starting point. Okay, the next point I want to make, okay, is that other number systems are possible. So we use one other number system all the time, and that is the duodecimal number system. Number systems based on 12, and we use that for clocks. And if you go back in time, the base 12 was used more frequently than it is at the moment. When I was born, okay, we used it for money as well. We had the shilling, okay, which is 12 pennies. And the reason why the duodecimal system was used was because it was very handy for trade. You could divide it by 2, 3, and 4. The decimal system is hard to use, okay, for trade because you can divide it by 2, but not by 3 and 4. But the point here is that other number systems, other bases are popular. And modular arithmetic is a branch of arithmetic that enables you to move easily, okay, between bases. So I became very fond of modular arithmetic when I started learning Python 7 or 8 years ago. The percent operator, which gives you the remainder, is very handy for moving from one base to another. Okay, so computers, humans have 10 fingers, and that seems to be the reason why we use base 10. Computers have 2 fingers, okay? And they count in 0, 1, 10, 11, 100, 101, 110, 111, 1000, 1001, 1010, 1011, 1100. Sounds very confusing, okay? But the pattern is exactly the same. So what I've done here is I've repeated the first slide that I showed you, but with the binary number system. And what happens here, okay, is 1, 0 is 2, because it's 1, 2 plus 0, 1s, and 0, 1 is 1, 1, and 0, 2s. And if you add those, you get 1, 1. And you can do the carry in exactly the same way. 1 plus 1 is equal to 0, carry 1. And this math is identical to the math that you learn in school, but it's to the base 2. Now, I want to make a very important point here. All computers work to the base 2. Every computer on the planet works to the base 2. We are going to talk about dotted decimal notation. We're going to talk about hexadecimal notation. We're going to work in other bases, but that is only to help humans. It is very important to realize that underneath the computers are using base 2. Computers only use base 2. If you think there are exceptions to that, you're wrong. Computers use base 2. When computers are working on a Word document, they're storing stuff as numbers to the base 2. Computers work in no other base but to the base 2, and they work in nothing else other than numbers. So computers have 2 digits, okay? I've made the point. Computers always work in binary numbers. The only joke I'm going to crack in the entire presentation is at the end of that slide. There are 10 types of people in the world, those that understand binary and those that don't. If you understand the joke, then you get what I've covered so far. Okay, so if you don't, I'm sorry, you're lost already. Okay, so binary numbers. So binary numbers are made up of bits, and a bit is a binary digit. And if you have 2 bits, a bit can be represented by whether a transistor is turned on or off. It has 2 states. So if you have 1 bit, you have 2 states. If you have two bits, you have 4 states. If you have 3 bits, you have 8 states, and it's 2 to the power of the number of bits. Now, if you want to work on a daily basis in IP addressing, you need to learn the table on the left. It's a bit like what you would do in school. And I used to be able to do a party piece where I could go into the millions on this. I got something missing there, sorry. It's 1, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, and so on. But you need to learn up as far as 1024. Now, the question is, if you have the number of bits, how many addresses can you have? Because we're solving the addressing problem here. And Nick has mentioned IPv4, which is 32 bits. And 32 bits means that you have 2 to the power of 10 multiplied by 2 to the power of 10 multiplied by 2 to the power of 10 multiplied by 2 to the power of 2. And that works out as 1024 by 1024 by 1024 multiplied by 4. But an easy way, my screen is covered with the camera here, so I just need to move it. An easy way, okay, to get an approximate answer to the number of bits is to take the 1024 as 1,000, and that means that you have 4 billion. Nick gave us the correct answer earlier, but it's just under 4.3 billion. But a good approximation is for every 10 bits, you get 1,000. Now we use this every day. A kilobit is 1,024 bits, but we call it 1,000. A megabit, a megabyte, we round them down, okay? Now, as the numbers get bigger, the rounding becomes larger, but it's a very useful way of getting very quickly. So if you learn the math behind this, then, you know, if you're given a number 2 to the power of 43, okay, then it's very easy I can call out straight away 2 to the power of 43 is 8 with 4 batches of three zeros after it. Now, I'm going to just mention MAC addresses today. Every device that's manufactured gets a hard-coded MAC address, and we have 248 MAC addresses. 2 to the power of 8 is 256, and then 4 by 1,000 means it's approximately 256. Nick has also given us the correct figure for IPv6. It's got 218 bits, and the actual number is written below there, 340 trillion. My approximation comes in at 256 trillion, so it's down by 50% once you get up to that size. But that number is absolutely astronomical. So I've seen calculations as to how many IP addresses that gives you per square centimeter of planet Earth. And I think it's in trillions per square centimeter. So in theory, at least, we're not going to run out of IP addresses on IPv6, but I'm sure in 20 years' time, it will seem obvious that could happen. Okay, so how are we going to deal with binary numbers? Binary numbers are very long. I've written down one IPv4 binary number, and I've written down one IPv6 address, and 010101000000000. It's very, very difficult, even though that's the way the computer works. So we need to get a shorthand. We need some way of dealing with those numbers. And the first thing that we're going to do, okay, is we're going to break those numbers up into groups of 4. And with 4 bits, we get 2 to the power of 4, okay, which is 16 possible values. And those, if we were to represent them as numbers, they would be from 0 to 15. And you can see the combinations of the 4 bits that give us that. Now, what we're going to do is we're going to convert those into digits that we recognize. We already have digits from 0 to 9. We don't have digits for 10, 11, 12, 13, 14, and 15. So what we're going to do is we're going to substitute the alphabetical letters A, B, C, D, E, and F. Now, a hexadecimal digit represents 4 bits, and those of you that are into computer science will recognize that as a nibble. So a nibble of data is equal to 1 hexadecimal digit. And it's represented by the characters 0 to 9 and A to F. Now, one unusual thing about hexadecimal numbers is that when you put them together, you can actually spell letters of the alphabet. You can spell words. So I chose dead and cafe here. I thought they were particularly relevant for a COVID-19 environment. So I've added the 2 numbers dead and cafe. And on top of the screen there, you can see, okay, that D, for example, is equal to 13 in decimal notation, and we're back to the carries. So this is identical to the first slide I started out with. It's just working at 16 to the 0 or 16 to the 1. And on the right-hand side, I have represented the decimal numbers that relate to those hexadecimal numbers. If any of you is masochistic, you can come back and stop the talk at this level and actually work out that sum yourself. So you can add 2, 3, 4 to 9 ABC. And I've actually worked it out for you on this slide. You can do it with a calculator quite easily. There are 2 carries. Just to get the naming conventions out of the way, we know what a bit is. It's a binary digit. 4 bits is a nibble, and that can be represented by 1 hexadecimal digit. 8 bits is an octet, is equal to a byte, and it can represent 2 hexadecimal digits. And 16 bits is a hextet, which is 1 word, and it contains 4 hexadecimal digits. And a hextet, is a word that was made up relatively recently. So I noticed that Word doesn't see it as in spelling checker, it sees it as being incorrect. And it is a makey-uppy word, but it seems to have kind of gained traction within the industry for a 16-bit section of an IPv6 address. Now, just very quickly, if you turn over a lot of networking devices, you will find a MAC address. And MAC addresses are encoded hexadecimally traditionally. So this is a photograph I actually got from the internet to save me having to take a photograph, but it's at the underside of a Cisco router, and it has the MAC address for that router. And I'm describing that address here as a PPS number. What that means, okay, is that that number doesn't change. It's locked into the device. It's hard-coded into the device. So if you move, okay, from Cork to Limerick to live, your PPS number follows you. Your address, you know, your postal address doesn't follow you, but your PPS number does. If we count up the number of digits, we will find, okay, that there are 12 digits in a MAC address. That means it can be represented, it's 12 hexadecimal digits, so that means it requires 48 bits. The next point that I want to get to, okay, is the fact that you can split addresses into parts, and the hexadecimal MAC address is split into 6 digits called a prefix and 6 digits called a postfix. And this is like what was described by Nick earlier, okay, for address and hosts. You have approximately 16 million prefixes. And the prefix in this case represents a manufacturer. So there's a website called macvendors.com. You can go there and type in a MAC address and it'll tell you who the manufacturer is. And I actually visited the standard, which is published by the IEEE. They maintain the list of manufacturer prefixes. And I've copied the record, okay, from that database in there as well. We will mention MAC addresses once more later on because they kind of come in a little bit in an IPv6 as well. Okay, IPv4 addresses. IPv4 addresses did not use hexadecimal numbers because back in the 70s, they thought it would be easier, okay, for people to work with decimal numbers. But the number that it represents is actually a 32-bit number. And IPv4 addresses go from 0 to 255 for the reason that you can represent 256 numbers going from 0 to 255. And it's just a kind of a technique, okay, to cope with the fact that us humans learn base 10 when we're in school. Right. So again, Nick covered this, okay, you've got a prefix which represents a network and that's what you use for external routing, and you've got the host part. And I randomly picked /18 here so that 18 bits are associated with the network and 14 bits are associated with the host. If you add the 14 and the 18, you must get 32. The point I want to make here, and this is a common problem in dealing with addressing, okay, is you've got a boundary problem. If you look at an address 10.1.1.0/18, a lot of people assume that it starts at 10.1.1.0, but in fact 10.1.1.0 is in the middle of that network. It's in the middle of that subnet. And I'm going to ask you to work that out yourself in your own time because we are a couple of minutes behind time. But that /18, okay, actually starts at 10.1.0.0.0. That's a problem for anybody. You can contact me privately and we'll discuss it. So IPv6 addresses, the decision was taken to go with 128 bits. Dotted decimal would have been way too long, so they wanted a more concatenated version and they moved to hexadecimal. So you need to be somewhat familiar with working in base 16 arithmetic if you're going to work in that environment. I can't even write 128 bits on the screen here, so I don't know how many bits I managed to write, but I ran out of space. And it's even difficult, okay, to write the hexadecimal version, okay, which is 4×8, which is 32 hexadecimal characters. The first 3 bits, okay, must be 001 for now. Other values are reserved. The plan, okay, to utilize IPv6 addresses, I think only about 12% of all IPv6 address space has any plan associated with it. So there's the possibility to increase. Nick mentioned RIPE, okay, so RIPE has a large number of /23s available for it. And as an example, RIPE has received 2A00:000:/12. We'll come back to the : in a minute, but the /12 includes a large number of /23s within it. if I'm doing the math correctly, it's 11, which would be 2048 /23s. But anything that starts with 2A00 is going to be from RIPE. Now, Nick mentioned RIPE as a regional internet registry. So CIX is a LER, is a local internet registry. So we can apply for IP address space from RIPE, and we can do that on behalf of our customers. There is no more IPv4 address space available. It ran out about 3 years ago, so you have to buy it on the open market from somebody that has it and then ask RIPE to pass it over to you. So for the last 3 years, Cork Internet Exchange has gone out and purchased IPv4 address space. The first /48 bits are the site prefix. So if you're an ISP, okay, then you get a /32. /48 is called a site prefix, and it's what you give, the first 48 bits, okay, or what you give to your, possibly to your customer, or if you're a multinational corporation, to your building. And a subnet prefix then, /64, is a particular project within a building. It might be your management network, it might be your finance network, whatever. I don't think there's a BGP reason, okay, why you can't route. Nick will be more experienced in this than I am, but anything below 64 on the public internet, but I don't think it's recommended. It's a bit like the /24 on the IPv4. Okay, so the remaining 64 bits inside in each subnet are available to you, and that's approximately 2 by 10 to the 19. So every subnet within IPv6 itself is absolutely enormous. And you know, within your business, there's nothing to stop you, okay, subnetting that down further. But on the public internet, as a matter of practice, it's not divided below that. Now, because the addresses are very long, okay, there's a policy, okay, for compression to make them shorter to write. So if we take a look at this IP address here, you can first of all, you can move leading zeros, and you can take the longest continuous batch of zeros and remove them and replace them with colons. So those 3 addresses are the same. And all we've done, okay, is reduced the number of zeros because it's wasted information. So be careful, you can't remove following zeros. You can only remove leading zeros because it would cause confusion if you removed the following zeros. And you can only concatenate one set of zeros, the longest set of zeros. So all you've done, you haven't lost any information in that concatenation. You simply have reduced the number of characters necessary to write it down. So just to give you an example, here's a loopback address in binary, the IPv4 for your if you want to ping 127.0.0.1, you're pinging yourself. And there it is in binary, and there it is as a dotted decimal notation. And I just chose this one because I think it's very interesting. If you apply the rules, okay, for concatenation, you can put all the zeros together and you can reduce leading zeros, and you ended up with an IP address which is : : 1. And what's interesting about this is because of the concatenation rules, the loopback address in IPv6 is actually shorter than the loopback address in IPv4. There are lots of different types of IPv6 addressing to cope with all the different protocols, okay? So what we've done is we've just very quickly talked about aggregatable global. If you ask your PC, okay, for your IP address, it will also supply you with a link local IP address. We're getting very low on time, so I'm actually not going to cover this slide. I want to leave at least a couple of minutes, okay, for questions and answers, but this is how the link local address is calculated. And we're just going to skip it for today. But the slide is there, and if somebody wants to ask questions on it or come back to me on it, that's fine. There are 2 ways of calculating the linked local address. One is using random numbers and the other is using EUI64, which basically takes your MAC address and puts it into the middle of the host bit. Let's move on. Okay, so I said that the objective was to get to where you would understand the IPv6 plan in CloudCIX. Okay, so we had a burning platform, IPv4 addresses. Last year we bought them for $20. Nick is now telling us, okay, that they're up in the $30 bracket. So the inflation in the last 12 months has been 50%. That's a bit scary. And we're starting to run short of IPv4 addresses again. So the problem that we really had, that we were facing, is we're building a global multi-region cloud, you know, involving public cloud, okay, with a franchise model with partners. We're offering private regions to companies that want to run private infrastructure, and complete private cloud to people who don't want to even share metadata. So this is a major project that just the management of it alone, okay, requires a lot of IP addressing. And our solution, okay, we decided to build CloudCIX as the management of CloudCIX on IPv6 from the start. So the project started about 4 years ago as an IPv6 project, and we also offer IPv4 addresses for free, whereas going forward you will have to rent an IPv4 address as you do in Azure and Amazon, whereas you get the IPv6 address for free. So that's the business case behind the IPv6 plan for CIX. And this is the IP address plan for CIX. So RIPE gave us a 2A02.2.078/32. And our business is divided into two. We've got colocation and we have CloudCIX. So we took a single /48 for colocation. We use a /32 of that to manage our own infrastructure. And then we assign /32s on the basis of the Fort hextet on a 1 per customer basis. For our cloud regions, we then have use the 3rd hextet to define the region, and we can use these, okay, for private clouds for companies, for private regions if they wish, not just our public cloud environment. And what you see on this screen is actually the IPv6 map, or the top level IPv6 map for CIX. If that map makes sense to you, then I have achieved my objective. If it makes some sense, I have achieved some of my objective. And we're coming up to 1 o'clock, so I want to hand it back to Owen there in case there are any questions and so on.
Thanks a million, Jerry. Excellent presentation. Excellent presentation from Nick as well. I'm just going to launch the second of our audience polls as well, and if we get a chance, we'll launch our 3rd audience poll. And I will also just look at some of the questions, and thanks to Nick, who has been answering some of the questions that have come through as well. A question for both of you, both of the panelists. This is from Shane Hartigan. What mechanisms are available to translate IPv6 to IPv4 for a network that is using NAT?
I'll take that one. So there's NAT64, which kind of converts between the two. There's no direct protocol compatibility, which is in general fairly difficult, and this actually gets into one of the questions that Jerry Kelleher asked earlier about what's the main thing that's stopping IPv6 from being rolled out. The answer is backwards compatibility. I mean, there are technical issues with the protocol, but really the issue is backwards compatibility, and that gets back to the fact that there's no clear way of moving from IPv4 to IPv6. You have to start off with IPv6 and deploy it. So it's a bit of a difficult area. Okay,
thanks, Nick. Jerry, do you have anything to add to that one?
No. Nick is the expert on IPv6. I'd leave a question like that to him.
Okay.
But it is a problem, and I think there's a couple of different NAT solutions depending upon whether you're an ISP or whatever. But Nick probably might jump in on this. But one of the big issues that, say, telephone companies are going to have to do is offer an IPv6 only service, but give a backdoor to IPv4. I don't know if Nick has a, but to me, it's the service providers who are going to have the biggest problem. Would you agree with that, Nick?
Yeah, absolutely. And in fact, some service providers actually do that already using technologies like DS Lite and Zoom. What can you do? So it is something that exists, but it's got issues because you're always dealing with protocol translations. So it's not an optimal solution. You just want either IPv4 or IPv6 only connectivity.
Very good. I'll try and squeeze in another question or two. And thanks to everyone that has submitted their questions. Another question from Shane. On a Windows machine, which IP is used as a priority if both IPv6 and IPv4 are both available on the network card?
I think I can take that as well. We have a protocol for handling this, and it's called Happy Eyeballs. And the idea is that Windows or Mac OS or whatever will actually send packets out on both. It'll send out an IPv4 connection and an IPv6 connection, and it'll measure which one is the fastest in response. And IPv6 is actually weighted positively in some operating systems like Macs. So it will try to use IPv6 if possible, but if it can't, it'll fall back to IPv4. And all of this is invisible to the user. You never see this happening in the background, but it's there all the same.
Okay, excellent. I have a question here from Mike Fitzgerald. Early adopters of IPv4 may be large enterprises. What are your experiences and costs and resources involved, as well as elapsed delivery time?
If I can cut in there maybe. So within the data center, so you have to look at this from two different perspectives. One is if you're a consumer, if you're getting your connectivity from an ISP. If you're getting your connectivity from an ISP, then IPv6 adoption is very easy because Windows and Macs and every device is IPv6 compatible. You don't have to configure anything very difficultly. It will be dual stacked. It will work in both. So what's happening in CIX at the moment then is we're getting more and more customers that need to become dual stacked, and we're finding that we need to be dual stacked. So even though I said that we were going to be IPv6, okay, for the entire management of our cloud environment, our API needs to be reachable on IPv4 as well. So so if you're a consumer, there's no cost. And Nick said, go tell your service provider, okay, they have to give it to you. And if the service provider can't, then they're not a good service provider, and all of the IT equipment is pretty standard. The fun comes, okay, if you're a service deliverer. Now, if you can do something internally and you need IP addresses, then maybe you should go for IPv6. So if you have an IoT application, you kind of have no choice. You need to think in terms of having an IPv6 strategy, because you can't afford to pay, I'm assuming, 30 euros a pop, okay, for an IPv4 address. If you're going to have 1 million devices out there, then you need to invest 30 million to buy your IP address bases. That may make your business case unsustainable. So the difficulty is for the service providers. Some of them can actually offer services like the IoT one that I mentioned on IPv6 only. In other cases, they have to be dual stacked. If you're supplying APIs, if you're supplying websites and so on. So the cost, I think, is for the person providing the service. And it's very interesting in CIX, okay, we see our service provider customers as putting significant input into this over the last year or two because of the costs of IPv4. People have just said, we're not buying anymore. We have to figure out how to do this on IPv6.
Okay. Excellent, Jerry, thanks. I think numbers are just dropping off, so I think we better wrap up. If I was to just ask you both, Jerry and Nick, your final tips for anyone that may be grappling with this whole area, final tips on where can they get some more help and advice on the area of IPv6?
Okay, so right, if you're a consumer of infrastructure, so if you're a customer of a data center or a customer of a cloud, then you have to work, okay, with your provider. If you are If you're an end user, then you have to work with your ISP. So in both cases, you're talking about going to your provider. Now, there was a question at the start about how you get an IP address. Okay, well, all of the providers really that are worth their salt, they're all LIRs now, local internet registries like CloudCIX is. So you can get your IP addresses from there. I'm guessing that there's a couple of service providers on stream here. So if you're a regional ISP or if you're a provider of services, then unfortunately you need to understand how this works. You need to be able to deploy dual stacked infrastructure. So if you divide it into three, the guys that work with your supplier, whether you're getting hosting or being an ISP, if you're developing services, okay, then you've got to build in-house capabilities.
Okay, excellent. Thanks, Jerry. Nick, final thoughts on this subject?
Being an engineer, I'm a huge fan of just getting your hands on it and playing around with it. I think that's enormously important because it breaks down the barriers that otherwise you'll create and you'll put in front of you, and it's those barriers which are stopping everybody from deploying IPv6. Lots of organizations have it. If you have lots of different types of for example, Virgin Media connections or a connection from air, you might just have it on your network already. If you open up a command prompt and just have a look at your network settings, you might see that it's actually enabled already and that it might just be there. So play around with this. If you're in an enterprise, do a deployment. Absolutely, do it quietly. It doesn't need to be a huge start. It doesn't need to be something that you throw huge amounts of investment at to start out with. And even for a full-scale deployment, you can get your firewalls in place. All firewalls will cope with this already. So just get out there and do it, is my advice.
Excellent. I'm going to launch our final audience poll, and while that poll is live, I'm just going to say thanks a million to both of you, to both Jerry and Nick. Thanks for taking the time to prepare the presentation. It's been very useful, and thanks to all of the audience, everyone that's dialed in at lunchtime as well. I hope you found this useful. As I said, we'll make the recording available in a week or so. We'll also make the results from our audience polls available as well in a week. Any other questions that we didn't get around to, we will also, I'll try and have a debrief with the panelists and answer any questions that we didn't get around to. So thanks very much everyone for dialing in. We appreciate your time and we hope to see you again. Thank you.